we're going to be talking about how substances move through cell membranes, which is happening all the time, including right now in me and right now in you. And this is vital to all life because it's not just how cells acquire what they need and get rid of what they don't, it's also how cells communicate with one another. Different materials have different ways of crossing the cell membrane, and there are basically two categories of ways. There's active transport and there's passive transport. Passive transport doesn't require any energy, which is great because important things like oxygen and water can use this to get into cells really easily. And they do this through what we call diffusion. Let's say I'm finally in this show, and I'm in the show with my brother John. Some of you know my brother John, and I love him, but he's not a big fan of people. I mean, he likes people. He doesn't like big crowds, being parts of big crowds with people standing nearby him, breathing on him, touching him accidentally, that sort of thing. Because John's with me at the show, we're hanging out with all of our friends near the stage, but then he starts moving further and further from the stage, so he doesn't get a bunch of hipsters invading his space. That's basically what diffusion is. If everyone in the club were John Green, they would try and get as much space between all of them as possible until it was a uniform mass of John Greens throughout the club. When oxygen gets crowded, it finds places that are less crowded and moves into those spaces. When water gets crowded, it does the same thing. It moves to where there is less water. When water does this across a membrane, it's a kind of diffusion called osmosis. This is how your cells regulate their water content. Not only does this apply to water itself, which, as we've discussed, is the world's best solvent. You're going to learn more about water in our water episode. It also works with water that contains dissolved materials or solutions, like solutions of salt water or solutions of sugar water or booze, which is just a solution of ethanol in water. If the concentration of a solution is higher inside of a cell than it is outside of the cell, then that solution is called hypertonic, like power thirst. It's got everything packed into it. And if the concentration inside of the cell is lower than outside of the cell, it's called hypotonic, which is sort of a sad version of hypertonic. So like with Charlie Sheen, we don't want the crazy manic Charlie Sheen. We don't like the super sad, depressed Charlie Sheen. We want the in-the-middle Charlie Sheen who can just make us laugh and be happy. And that is the state that water concentrations are constantly seeking. It's called isotonic when the concentration is the same on both sides, outside and in. And this works in real life. We can actually show it to you. This vase is full of fresh water, and we also have a sausage casing, which is actually made out of cellulose. And inside of that, we have salt water. We've dyed it so that you can see it move through the casing, which is acting as our membrane. This time-lapse shows how over a few hours the salt water diffuses into the pure water. It'll keep diffusing until the concentration of salt in the water is the same inside the membrane as outside. When water does this, attempting to become isotonic, it's called moving across its concentration gradient. Most of my cells right now are bathed in a solution that has the same concentration as inside of them, and this is important. For example, if you took one of my red blood cells and put it in a glass of pure water, it would be so hypertonic, so much stuff would be in the cell compared to outside the cell that water would rush into the red blood cell and it would literally explode. So we don't want that. But if the concentration of my blood plasma were too high, all the water would rush out of my cell and it would shrivel up and be useless. And that's why your kidneys are constantly on the job regulating the concentration of your blood plasma to keep it isotonic. Now, water can permeate a cell membrane without any help, but it's not actually particularly easy. As we discussed in the last episode, cell membranes are made out of phospholipids. And the phospholipid bilayer is hydrophilic, or water-loving, on the outside, and hydrophobic, or water-hating, on the inside. So water molecules have a hard time passing through these layers because they get stuck at the non-polar hydrophobic core. That is where the channel proteins come in. They allow passage of stuff like water and ions without using any energy. They straddle the width of the membrane, and inside they have channels that are hydrophilic, which draws the water through. The proteins that are specifically for channeling water are called aquaporins. Each one can pass 3 billion water molecules a second. Makes me have to pee just thinking about it. Things like oxygen and water that cells need constantly, they can get into the cell without any energy necessary. But most chemicals, they use what's called active transport. This is especially useful if you want to move something in the opposite direction of its concentration gradient, from a low concentration to a high concentration. So say we're back at that show, and I'm keeping company with John, who's being all antisocial in his polite and charming way. But after half a beer and an argument about who's the best Doctor Who, I want to get back to my friends across the crowded bar. So I transport myself against the concentration gradient of humans, spending a lot of energy dodging stomping feet, throwing an elbow to get to them. That is high energy transport.